The research that I'm presenting to you today is tannic acid as a modulator of nisin release from Nanochitosan matrices. So, the basis of our research was derived from the fact that many cosmetic products in their industry have preservatives that are not quite foolproof. A lot of cosmetic products don't have long lasting shelf lives, thus spoiling faster. Thus, to combat this, we tried to find an organic preservative that would serve as an alternative to recent preservatives that are in the cosmetic industry today. Upon researching, we found that nisin would serve as a preservative in cosmetic products, particularly creams in our case. So, what nisin is a polycyclic antibacterial peptide that protects against other bacterial species. It comes from Lactococcus lactis. It also has a broad spectrum against different gram-positive bacteria. It serves as an antibiotic, but the problem is it tends to leak in lipid-filled fatty environments. So, in order to take this from the creams to the skin, we had to find a carrier. So, the carrier that we found was chitosan. Chitosan comes from natural biopolymers, chitins, from shrimp cells. They're also inexpensive, they're antimicrobials, they're antioxidant, they're biodegradable, and they're biocompatible. However, being that nisin has the problem of leaking in fatty environments, we had to find a crosslinker. This is where we introduced tannic acid. Tannic acid is an ester that has multiple phenolic groups with the ability to crosslink. It also has the ability to form complexes with proteins. It is a strong antioxidant, a strong antibacterial property, and has strong anti-mutagenic properties. So our objective is to kind of force a modulation of release by the complexation of tannic acid. So how we prepare these chitosan nanoparticles is by the ionic gelatin method. And just to quickly go through, we prepared zero point 0.5 chitosan in 1% acetic acid. We adjusted the pH to 4.5 using 1 molar of NaOH. We ultrasonicated for 30 minutes, then used a magnetic stir for 24 hours for complete dissolution. We then added nisin and tannic acid, ultrasonicated for 45 minutes, and then added 0.5% sodium tripolyphosphate. We then magnetic stirred for 1 hour, centrifuged at 900 RPMs for 1 hour. Then we separately collected the supernatant and the precipitate. Then we spread the precipitate across the glass and we let it dry in a desiccator. And once it dried, we then grinded it to get our nanoparticles. So basically, from our nanoparticles, we had received 11 samples. Five of them are which are nanochitosan only with nisin only, ranging from zero point 0.5 mg per ml to 4 mg per ml. Then we have another five which contains nanochitosan, nisin, and tannic acid from zero point 0.1 mg per ml to 4 mg per ml. And then we have just regular chitosan nanoparticles with nothing in it at all as a control. So from this, we conducted five different tests. First, we used UV spectroscopy in the filtrate to see how much nisin was encapsulated. Then we used the ratio of residual amino groups, which is RAG, through colloidal titration to measure cross-linking in nanoparticles. We then use Fdrs Spectra to determine the presence of functional groups and the effects of cross-linking. And then we use the antimicrobial assay to determine antimicrobial activity and an antioxidant assay to determine the antioxidant activity. So the tests that I'll be focusing on are going to be the UV spectroscopy test, the colloidal titration, and the FTRA spectra. So from the UV spectroscopy and the colloidal titration, we can see how much nisin was encapsulated into the particles. And from here, we have encapsulation efficiencies ranging from 85 to 91%, showing that there's a successful encapsulation of nisin. And then from here, from the RAG numbers, we can also see that there was cross-linking due to the trisodium phosphate and the tannic acid. From here, I just want to quickly show the Fdrs spectra. And as we look at the nanoparticles containing tannic acid, we can see broadening around the 3500 area, which shows that there is oxygen and hydrogen bonding forming, showing that there's cross-linking. We also can see, just a little bit if you look, around the 2900 area, there's also carbon and hydrogen bonding as well, showing that there's more cross-link. And if we look a little further down, it's kind of hard to see, but if we look a little further down, around the 1200 and 89 and 890 part of the spectra, we can see that there is phosphorus and oxygen stretching and bonding. So that's also another form of cross-linking that we can see. So based on our conclusions, we can we can say that the ionic gelatin method was successful in creating nanoparticles using sodium triphosphate as a crosslinker. Colloidal titration with potassium polyphenol sulfate has shown significant cross-linking in all nanoparticles. All nanoparticles retain positive charge beneficial for their antimicrobial effect. As reiterated before, we can see that from the FTRI spectra, there was cross-linking based on the bonding and the stretching that we've seen. A previous study showed a strong dependence of the amount of nisin released over time from a carbon to nitrogen ratio. Tannic acid modulation potential has been displayed in the kinetics of the release results. All nanoparticles showed an antioxidant effect. Tannic acid alone had a high antioxidant activity, but it did not impart the expected increase to the antioxidant activity of the nanochitosan particles with tannic acid in it. This may be due to a different order of magnitude concentrations of tannic acid in the nanoparticles compared to a tannic acid only sample. And continued, nanoparticles with added tannic acid displayed increased antimicrobial activity compared to those containing only chitosan and nisin. The nanoparticles compared in their singular components showed increased inhibitory activity. The nanoparticles were successful in inhibiting the growth of broad range microbial species. These are the species that we tested against, which was E. coli, S. aureus, and P. aeruginosa. The MIC, which is the minimum inhibitory effect values, were lower for all compositive compared to the individual components demonstrating synergetic effects. This is remarkable since nisin, whose concentration had an important impact on the MIC values, is effective only against gram-positive species. So in the future, we plan to test the influence of the size of the nanoparticles on the antimicrobial activities, which will be investigated, as well as we will investigate this further on in creams. Thank you. And I just want to say thank you to Dr. Leonida, thank you to the university, and thank you to Dr. Benzecry.